Good morning, fellow mathematicians. Welcome back to another video. So we are doing something I haven't done in a while. It's going to be an improvised session because a subscriber of mine actually sent me something that looks quite interesting. So I hope you can actually see it. It's from our boy Adam Cohen. And my stepbrother just sent me a message. So now you know how he looks, probably. Yeah. We're going to give it a shot. I'm going to get myself a piece of chalk and then we're going to see where we are going to get. So if we can actually solve it, because it looks quite spicy actually. And he said that it's going to yield Apery's constant. I guess it was zeta of something. So yeah, we're going to give it a shot. Give me a second. So improvised session means that I don't really know what I'm going to do. We are just going to give it a shot. We are going to try out several things, and up until now all those improvised sessions turned out quite okay. Mostly with the right answers in the end. So yeah, we're going to give it a shot. So what was the integral? Still the blue chalk right here. From 0 to 1 of the natural log of x times the natural log of 1 plus x over x integrated with respect to x. So I already thought of one or two things we could possibly do while being in the bus and checking my email. This mail was from 2 days ago actually. So yeah. So what I thought was just simple integration by parts, because we can differentiate the natural log of 1 plus x. And we can actually integrate this other part right here. So ln x over x is pretty easy to integrate. So if we take a look at the integral of ln of x over x, well, obviously if we just said, I don't know, it really doesn't matter if we substitute t being equal to natural log of x, then this is going to yield that dt is nothing but dx over x, and you immediately see that this is just this part right here. So if you put a differential in here, then it actually is. So we are going to integrate just t dt in this case, I'm terribly sorry, and this is going to yield t squared over 2, but t is nothing but natural log, so natural log squared of x over 2. If we plug this in. So we have to differentiate something and we have to integrate something, plus minus differentiating the natural log of 1 plus x. It's going to give us 1 over 1 plus x. Inner derivative is just 1, so that's good. And integrating this thing right here. So ln x over x, we know that this is going to weigh to the natural log squared of x over 2. Multiplying this together, taking the integral of this thing, is going to give us the following. So we are going to get the natural log of 1 plus x times the natural log squared of x over 2 from 0 to 1, and then minus this chunk multiplied together as an integral. So minus, those are just side notes, the 1/2 to the front is just a constant, so integral from 0 to 1 of natural log squared of x over 1 plus x integrated with respect to x. Obviously, if we plug 1 into here, this is going to vanish. If we plug 0 into here, this is a 0 times negative infinity situation. So we can probably use L'Hopital. Let me see if something grows faster than another piece. So if we plug 0 into here, this goes to this goes to infinity. That's a good question. What is going to grow faster? I'm going to leave this for a second. We're going to do some L'Hopital shit in a minute. Let me see what we can actually do here. So that's the main thing, I guess. I guess this is going to vary to 0 in the limit. I could be mistaken. Maybe it's unbounded. I really don't know. But what do we have here? Isn't that something I already evaluated at some point? It looks like something I already did. So what we can basically do, this is nothing but the natural log squared of x times our geometric series of -1 to the kth power, so we have k being greater or equal to 0 times x to the kth power. Okay, this is what you would have right here. But is it easy enough to integrate this thing right here? That's a good bloody question. So the thing is, I'm thinking here right now. The thing is, I mean, we can turn it into a Taylor series. That should work out. But couldn't we just turn something here into a Taylor series? So either, I mean, 1 over x turning this into a Taylor series. Yeah, we don't need this at the moment. So we would have to do more work right here. But so for example, those two right here, we already did basically Taylor series on that. So we did a Maclaurin series expansion of that. I still have to think about what that actually is. And yeah, we can just shift some stuff right here to actually get our Taylor series for the natural log. So I'm thinking, is it easier to integrate this thing by parts then, or by doing a Taylor series expansion on here? So I mean, either way, our Taylor series expansion does exist on this interval, and we can safely interchange our integral and this infinite sum right here, this series, this infinity boy, because on this interval where the radius of convergence holds, this thing converges uniformly, so that would be okay. Let me see if this works out. So what's the Taylor series for the natural log of 1 plus x? So if you differentiate this, so the first term is going to vanish if we evaluate this at 0, okay? This does make sense. So overall we are going to get an infinite sum running from 1, okay? I'm using this notation, this just means running from 1 to infinity, okay? That's still the regular infinity boy that you all know and love. Maybe I should make a limited edition version where we have this greater or equal to 0 right here. Okay. We are definitely going to get an alternating series, so that's something that we have. On the first term, we are actually going to get a positive sign, meaning we have to have k plus 1 up here. Also, we are going to have this x to the kth power term, so that's something that comes quite natural. Oh yeah, and then we were actually generating those k factorial terms, but this is going to give us k minus 1 factorial overall. So you see, I made a video on that, so this k minus 1 factorial and k factorial is going to cancel out to just k in this case. Okay, that should be the Taylor series for the natural log of 1 plus x. If we would plug this into here, we are actually going to get, for our integral I, I'm going to give it the name I right here, because why the hell not? We are going to get that this is integral from 0 to 1 of natural log of x over x. You see, I only get the idea because Taylor series would probably work out here, so we could actually also start right here with the Taylor series. So that's something that probably does work out here. We are just going to give it a shot. In those number theory, I would say analytic number theory integrals, if it really does yield something with zeta, then it's always a good idea to turn something into a series. That's probably the way to go. Okay, then we are going to get the sum from 1 to infinity, the infinity boy, negative 1 to the k plus 1 of power, x to the kth power over k integrated with respect to x. Like I said, on this interval, on the radius of convergence, it does converge uniformly. And absolutely, I don't know, I guess just absolutely. Yeah, it does converge absolutely. And we can thus interchange the summation, this limit and this integral. Also, we can bring those two constants to the outside, to the front. So we are going to have the infinity boy of negative 1 to the k plus 1 power over k. It actually does look right now as if we are going to get ourselves the Dirichlet eta function, because in here there's no way to actually get a negative 1 to the kth power somehow back. So I guess you can already see it. So we are going to end up with an alternating series. So there's nothing that can actually cancel out our negative 1 to the kth power right here, so that's going to be an alternating series overall. Integral from 0 to 1 of x to the kth power, and this is going to be x to the k minus 1th power, so we are going to have natural log of x to the k minus 1th power dx. And yeah, now it's quite obvious how we are going to do integration by parts, okay? Because finding the antiderivative of natural log is kind of elementary, but not something we do in the normal case, so it's way easier integrating a polynomial than integrating a special function, I would say. So differentiating the natural log gives us 1 over x, and you see it's going to work wonders, because now we have x to the k minus 1th power. Integrating this leaves us with 1 over k, because we have to raise the power by 1, times x to the kth power. So x to the kth power over k. Okay, let me see where this is going to get us. Infinity boy. Negative 1 to the k plus 1th power over k. You can also do negative 1, okay, k to the negative 1 to the k minus 1th power. It really doesn't quite matter right here. And then we are going to have integral from 0, no, we are doing integration by parts, I'm terribly sorry. Meaning natural log of x times this chunk is going to give us natural log of x to the kth power over k from 0 to 1, negative, I'm going to bring the 1 over k to the outside using the linearity of the integral, and then integral from 0 to 1 of x to the k minus 1th power integrated with respect to x. Okay, evaluating this thing is quite easy. We just basically did that. Why did I have a k plus 1 right here? I'm terribly sorry. K minus 1. Yeah, this thing is just going to evaluate to 1 over k times x to the kth power from 0 to 1. K starts at 1, meaning all those terms in this series are going to have some x term, meaning on 0 it's going to vanish, and 1 to every power is just 1. So overall this is going to give us negative 1 over k squared. Okay, this is something we are going to get. Yeah, negative 1 over k squared. Yes. Okay, negative 1 over k squared. Now let's think about this. So if we plug 1 into here, this thing is going to be natural log of 1 is nothing but 0. If we plug 0 into here, this is actually negative infinity times 0 situation. So what we can do, we can actually, okay, let me erase something. We are going to use L'Hopital on this thing, and that should actually work, I guess. Okay, yeah, we are just going to take a look at the limit. I'm going to denote this limit by capital L then. So we are going to get the limit of, okay, we have to turn this into a fraction, otherwise we can't use L'Hopital. I guess it's easier to put this x to the kth power in the denominator, making it 1 over x to the kth power, so x to the negative kth power. So the limit as x approaches 0 of natural log of x over x to the negative kth power. If we differentiate top and bottom with respect to x, we are going to get limit of 1 over x, and this is just a polynomial. So negative k times x to the negative k minus 1th power. If we drag this down, we are going to get a plus 1 on here. So yeah, we are going to get a plus 1. So this is the limit as x approaches 0 of, okay, this is just some constant. Let's just, yeah, doesn't matter. That's approximately the limit as x goes to 0 of, okay, this is going to give us 1 over x to the negative kth power is nothing but this limit of x to the kth power, and if this approaches 0, we are actually done. So this actually goes to 0 in the limit. So that's good, I guess. This whole thing is going to vanish in the limit, meaning this is going to give us overall sum running from 1 to infinity of negative 1 to the k plus 1th power. But we have this negative sign right here. I'm going to bring it to the front. Actually, yeah, I'm going to bring it to the front. and then we are going to have over k to the third power overall. Okay, yeah, like I said, this thing right here is nothing but the Dirichlet eta function, okay? This alternating series is going to be preserved in this case, so this is negative Dirichlet eta of 3, okay? In normal case you would have an s up here, but this is negative Dirichlet eta of 3. We actually found an expression for the Dirichlet eta function. I made a video on that one integral, but we can actually, since this thing converges for certain values, we can rearrange this into some kind of zeta function. That's kind of some alternating zeta function. So Dirichlet eta of s is nothing but the Riemann zeta function of s times some weird factor 1 minus 2 over 2 to the s power. Okay, meaning if we plug 3 into here, this is going to give us then zeta of 3, which is probably Apery's constant the boy was talking about, and then we are going to get yeah, this is 1/4, okay, 1/4 right here, and then we are going to get 3/4. So overall our answer should be 3/4 zeta of 3, but with a negative sign. Okay, so overall I is nothing but negative 3/4 Riemann zeta of 3. Or you can just say that this is nothing but Dirichlet eta of 3. Okay, negative Dirichlet eta of 3. And I hope this is correct. I'm pretty certain that the other approach should also yield the same thing. I mean, by the same argumentation with L'Hopital, you can probably let this one limit go to 0, and then you can just work further with this Taylor series expansion that I got. So let me just see. What would we need to do? We had this natural log squared term, meaning we can differentiate this to get, okay, 2 times the natural log of x over x, okay, and then we would have x to the kth power 1 over k plus 1 x to the k plus 1th power. This overall in the limit should once again vanish from 0 to 1. Then we would have this term, meaning we can differentiate this once more, leaving us with 2 times 1 over x squared, and here we are going to get 1 over k plus 1, k plus 2, x to the k plus 2th power. Okay, this should vanish in the limit once again, and then we are going to get this chunk, and you can probably do a change of variable then to actually get to what we want to have. Apery's constant right here, zeta of 3. So yeah, this should definitely also work out. So I could have proceeded from there, but starting off with a Taylor series from the start should also be pretty good, and you see it worked out. If you did enjoy this video, please like and subscribe and recommend this channel if you like. I hope my shirt didn't scratch the microphone right here. There would be sucky, sucky, fucky, fucky. You can buy those t-shirts I created, they are pretty dope actually, or you can click on those Quora questions I post from time to time to support the channel actively this way. And up until the next video, have a Flammable day. I hope this helped. Adam Cohen, see you later. See ya. See ya. I'm saying see ya all the time. See ya.